Okay, so can you just tell me what is this diagram listed here? Then we'll begin slowly. So, what is this diagram and why I had drawn this in the previous class? So, I told you that if you have a continuous system, with you, like say x dot equals to ax, okay, and you have, if I write x dot equals to ax, this is known as a 2D linear system, right? Why I am saying this is a 2D linear system? I'll just give you an example right now. X dot, suppose it is x and y. So x dot y dot, and you have a matrix. So suppose that matrix is 5, 3, 2, 8, and you again have x and y. Okay, just an example. So you know this is 5x plus 3y, and this is 2x plus 8y. So you can see that the rate of change of x with respect to time and the rate of change of y with respect to time is varying linearly in a linear fashion, that is 5x plus 3y and 2x plus 8y. Yes. So this is, therefore I told this as a 2D linear system, 2D linear dynamical system. Okay. For this 2D linear dynamical system, we can actually categorize different behaviors. Okay. What researchers found? What researchers found? Researchers found that when they change the entries of matrix A, that means instead of 5, they make it 6. Instead of 3, they make it -3. Then the total dynamical behavior of the system changes. Dynamical behavior of the system change. Okay, what do I mean by the dynamical behavior of the system? That means if you plot x and y, now, then suddenly you will see that, suppose you have a matrix A and you evolve your system, that is x dot and y dot, and you record those data points. Yes, how x is varying with time. Then you will, this is your starting point, this is the initial condition. And since it's a continuous system, it won't hop like this, right? It will go continuously like this. Yes. So for some, you will see that it is going like this, it is spiraling inwards. For some, you will see that, it is, if this is the initial condition, it is spiraling outwards. Okay, so this is the behavior you will see. In some behaviors, you might see that it is just coming like this. Okay, so these are the behaviors. In other behaviors, you might see that it is just going like this outside. Okay, so these are all the behaviors, possible behaviors you can see. And one other behavior is very interesting behavior. This is one behavior. So where you can have this circular orbits, where orbits repeat itself. They lie in this circle only. Okay. So many these kind of behaviors are possible, and all these behaviors are possible just by changing the entries or the numbers of this matrix A. Then researchers were baffled about this, like why such behaviors were occurring. Can we make a unified theory to understand all this? Can we make a unified theory to understand, like, yes, if this is the matrix, then this is the behavior. If this is the matrix, then it will be spiraling inwards. If this is the matrix A, it is spiraling outwards. If this is the matrix, we have this closed orbit. And if this is a particular matrix, then we have orbits like coming towards the origin, something like that. Okay. So how to categorize if only you have a matrix A? That is the basic idea. Note that this theory, this unified theory, only works for two-dimensional continuous systems, two-dimensional linear continuous systems. It won't work for 3D continuous systems or also 2D nonlinear systems. It won't work. Okay. So this is an example. What researchers came across is, to understand the matrix A, you can just look into the trace of that matrix. Trace and determinant of the matrix are inherently related to the eigenvalues of the matrix, and eigenvalues of the matrix play a central role in understanding the distinguishing dynamical behavior of the system. So you already know that trace of, what is a trace of a matrix? suppose I will just give a outline because just to make everyone be on the same page. So suppose this is the 2D matrix because we are considering a 2D system. Okay, we are considering a 2D system. So what is a trace of A? Can anyone say what is a trace of A? Trace of A is nothing but the sum of the diagonal elements. What is the sum of the diagonal elements? A. Then what is the determinant of A? That is, we denote by det A. Determinant of A is, how you compute the determinant of A? So you multiply these two guys, that is A into D, then you subtract them with B into C. Okay. Yes, so this is the determinant. Okay. But trace and determinant also has a different expression of eigenvalues. Okay. Suppose matrix A has eigenvalues. How many eigenvalues it will have? How many eigenvalues it will have? 2, because a 2D matrix will have 2 eigenvalues. Say it has 2 eigenvalues, lambda 1 and lambda 2. What do you mean by eigenvalue? Eigenvalue is a constant, is a scalar. Eigenvalue is a scalar such that Ax is equals to lambda 1x. Like, can you see what is happening? When you multiply a vector corresponding to lambda 1, you have a corresponding eigenvector. So if you multiply the vector A, if you multiply the matrix A and the eigenvector x, then the result will be a scalar multiple of that vector, and that scalar will be known as the. So this is an eigenvalue, lambda 1. Similarly, A y equals to lambda 2y. Okay, this is a different eigenvector. Okay, so this is the concept of eigenvalues. So if the matrix A has 2 eigenvalues, lambda 1 and lambda 2, then there is a relation between the trace and the eigenvalues, determinant and the eigenvalues. So you can write this A plus D. So trace here trace is related to the entries of the matrix. Here trace and determinant related to entries of the matrix. Okay, but now I will say to you how trace and determinant are related to eigenvalues of the matrix. No, that is other way around. Actually, trace of A is the sum of eigenvalues. That is same as, still it is the same as A plus D, and determinant of A is the product of eigenvalues. That is AD minus BC, it is still. So this represents a unified formula of the trace and determinant with the entries of the matrix and with the eigenvalues as well. Okay, so this is what is important. So scientists thought that computation of eigenvalues, you know that a 2D matrix computation of eigenvalues will involve a square root. Okay, it will involve a square root, and that is even more complicated. So scientists thought, why not we take the trace and determinant? Why not we take trace and determinant to classify the various dynamical behaviors of this 2D linear system? Okay, so therefore, motivated by this, they constructed a trace determinant diagram. What they did here? What they did is they constructed a trace determinant diagram. Why it is behaving a bit oddly? Yes. So the trace determinant diagram. So tau is the trace, and delta is the determinant of A. This is the notation we follow. Okay. And just by looking into this trace determinant diagram, you can classify various dynamical behaviors. Okay. What they did, just like some our mini project students are doing, they're doing a regime map. What they do in the regime map, like they have these two parameters tau and delta, and for different values of tau and delta, they are marking the regime, what regimes they are seeing. Okay, scientists did the same way. They started marking, yes, for this value of tau and delta, I see spiral. For this value of tau and delta, I see, yes, the node, or I see for this tau and delta, what other behaviors, different pairs. Then they came across this figure, which I just drew in the last class. They came across this figure. Okay. So they found that there is a curve that is tau square minus 4 delta equals to 0 that is behaving as a border case. Okay. Below that curve, you can see the spiral is unstable. An unstable spiral exists. What is an unstable spiral? You can see that it is going outwards. It is going outwards. If it is going outwards, that means you can see that yes, if I am an equilibrium point and you are spiraling outwards me, then yes, I am an unstable equilibrium point. Okay, it is moving outside. If you are spiraling towards me, then I am a stable equilibrium. Okay, so below the line, below the curve tau square minus 4 delta, below this curve you have unstable spirals. Above that curve, yes, okay, let me cover this. Below that curve you have unstable spiral in the first quadrant. Then you move to the quadrant below, you can see that the spiral is now inwards, like it is moving like this. Totally opposite behavior. So it is like converging to an equilibrium point. That is a stable equilibrium. So this is a stable spiral. Okay. So you can see that when the trace is positive. Okay, trace is positive and the tau delta point is below the curve tau square minus 4 delta is equal to, then you have unstable spirals. If tau is less than 0, that is on this case, and it is just above this curve tau square minus 4 delta equal to 0, you have the stable spiral. Okay, fine. Then what happens on this line, on this curve, exact curve, that is tau equal to 0? When tau, so on delta, on this axis tau is 0, right? On these axis tau delta is 0, right? Sorry, tau is 0. So when tau is 0, when trace is 0, you will see these periodic orbit looking circles. Okay, so this is the basic idea of this system. Okay, moreover, you can observe that above this tau square minus 4 delta equal to 0 curve, you have something like unstable nodes. So what you can feel, how you can remember this concept? If you can just remember this chart, if I give a matrix to you, then you can properly predict the dynamical behavior of the system. Okay, remember that whatever is lying on the first quadrant, is unstable. Whatever is lying on the first quadrant is unstable. Just above the tau square minus 4 delta equal to 0 curve, you have unstable nodes. Can you see why it is unstable? Yes, all this is the unstable node, right? And all the trajectories are moving outside of it. They are moving outside. Are they moving inwards? Are the trajectory moving outward or inward? Outwards. So therefore it is unstable. Yes. And the same replica you see just by the mirror image of the coordinate. That is this one. You can see the same thing, but now the trajectories are inward. So it is a stable node. So if you see this kind of behavior, it is known as a stable node. Identify this phenomena that these trajectories, if you start from here, then you see this, it is coming like as a tangential way. Okay. So that is the basic idea of this. So, and one more interesting case on the right side, on the left side, you can see when delta is less than 0. When delta is less than 0, you have something known as saddles. Saddles are like horse saddle. So on one way you can go like this, on another way you can fall like this. Okay? So it has both ways. It has a mixed nature. So yes. So it has a mixed nature, like you might have come across some persons who have mixed nature, right? So in the sense that to you they will be very friendly, but at the same time to them they will be very odd. Okay. Huh? I mean, Aparichit. I think you saw the movie Aparichit also. Aparichit, no? Aparichit. Huh? Huh? Vikram was there. Ah. There you see that he was behaving differently. So you see this concept here. Yeah. So this is a saddle behavior anyway. So this is what I told you, the classification, and this follows importantly. We will consider some examples of the matrix, and you will be telling me the behaviors of the system. Okay, let us start with an example. Um, maybe we'll look into a very nice example which involves a bit of math, but will be interesting. So let us start this example. Um, uh, Maybe we'll start with some linear thing. Let us move non-linear later. Just hang on. Okay, x dot is equals to 2x and y dot is equals to minus 3y. Okay, x dot is equals to 2x and y dot equals to minus 3y. Actually, the first bench is empty. X dot is 2x and y dot is minus 3y. It is a very easy looking equation, isn't it? Why? Because x is not depending on y and y is not depending on x. These are not coupled. These are not coupled systems. Okay, they are uncoupled systems. X is depending on x, y is depending on y. Each is minding their own business. Okay. So how you can solve it? So you can easily solve this, isn't it? So first let us look into this. Dx by dt is 2x. For bio AI people, I will do it very carefully. So try to listen this. So dx by dt is 2x. Okay. So what you do? Dx, you can say 2x equals to, maybe I will not bring the 2 here, let it be here. Then what I do, I brought it downstairs and then I will integrate here on both sides. Okay, integrate here on both sides, and you know integration of 1 by x dx is ln x, ln natural logarithm x. Okay, and this is 2t, and then you add a constant of integration. Okay. Yes. Okay, so at, you need to have an initial condition, isn't it? What is the initial condition? At time t equals to 0, x equals to x naught. You start from a particular point. So at t equals to 0, if you substitute t equals to 0, substitute. So ln of x naught is equal to 2 times 0 plus c, right? Isn't it? So c equals to ln of x naught. So therefore this equation 1 becomes equation 1 becomes what? Ln x equals to 2t plus ln x naught. I substituted this value onto c. So ln x minus ln x naught equals to 2t. So you can see ln x minus ln x naught is just this guy. Am I right? Yes, it's a division, and ln, it's 2t. Yes. Then there is a trick. There is a trick that how you can extract x. How you can extract x? Exponential. Okay. So this will be, might be new to you. So ln x is nothing but log to the e base. That is what natural logarithm is. And what we do is we take this e. Okay, the e flies over. Okay, you see how the e flies over. I think you know already. The e flies over here. The e will fly like this. Okay. So once the e flies, how it will look? So it is just, and you keep, this one will be there, this won't fly. So x minus x naught, and e has flown over, so e to the power 2t. Okay, then you already know x is x naught e to the power 2t. Like this, you have reached to the solution x. So x it is better to write x of t because it's depending on time, and it is x naught e to the power 2t. Okay. Similarly, can you say what will be this value? From this you got this. From this, what you will yt equals to? Similarly, you will have y naught e to the power minus 3t. Yes, that's just coming from common sense. Okay, now can you just by looking into this, can you predict how the solutions look like in your xy plane? Okay, so you just observe these things like how x is changing with time. X is changing with time as an exponential factor e to the power 2t. Okay, so you can see that now this is what I call a phase space. A phase space. That means we start in your phase space means you have x and y as the variables. You have x and y as the variables. X and y as the variables, right? And this is a phase space, we call it, because these are two variables varying over time. X and y are the two variables which vary over time. And to monitor how each is depending on each other, this is a phase space being created. Okay, this is known as a phase space. And since it's a plane, it is better known as a phase plane. If you move a dimension more than this two, it is known as a phase space. Okay, so how it will look like? Suppose you started from here. This is your x naught, y naught. This is your x naught, y naught. Can you tell me how this point will evolve with time? As time increases, how this point evolves? You can easily see that as time t tends to infinity, time is increasing, this guy will exponentially increase, isn't it? Exponential of 2t. At the same time, this guy, since it's minus 3t, this guy will exponentially decrease. Yes. So x is increasing and y is decreasing. X is increasing continuously and exponentially, and y is decreasing. So how it should look like? And it won't be linear. Will it be like this? No. It won't be like that. I'm not able to hear. Again. Upward. You think properly. If it goes upward, that means you are saying y is increasing. But y is actually decreasing, isn't it? How about this guy? How about this? Which color shall we pick? Maybe red. How about this? Does this make sense? Are you agreeing? Are you agreeing? Why? Miss Abhirami will tell. Why? Why this is true? Why this is working? Huh? X is exponentially decreasing, no? Yes, sir. X is exponentially increasing, no? You see, if X is value going like this, that means it's increasing. And Y is decreasing, no? So this is a plot for that. Yes. So how it will look like? You can consider point here. Think about this, how it will look like. Let me know. Take points here and think how the trajectory will look like. If these are your initial conditions, how it will look like. Take in 4 quadrants and let me know soon. Come on. Yes. So what you can do is, can you tell me how it looks? Does it look like this? This one look like this? Is it Saliman? Can you confirm this is correct? You did yourself. Huh? Which one? In the second quadrant here, x is decreasing. How x is decreasing? Yeah, you are in a confusion. I could see what is that confusion. Okay, let us see the second quadrant, for example. For the second quadrant, x is less than 0 and y is positive, right? Is it correct? Okay, then what is our solution? X naught e to the power 2t, right? And y naught e to the power minus 3t. So x naught is negative. This is guy is positive, and positive but big. Okay, positive but a big quantity. So you are multiplying a negative and a big quantity. Okay, so it is a negative but a big quantity. Okay, so where it should go? Negative. So minus 3 is here. Minus 50 will be where minus 50 should be. Minus 50 should be here, right? So that means as you increase the time, it gets bigger and bigger. That means it grows on this side. Is it clear now? Is it clear now? So this is something important from aptitude point of view also. So you can see that these are like kind of mirror images. Okay, let us be back. So this is how it actually looks. This is how it actually looks. Okay. So what we did here, we took different initial condition. Therefore, I asked you to do lot of initial conditions and see how it varies. Okay. If you lie on x-axis, you should think what happens if you lie on x-axis. What happens if you lie on positive y-axis and negative y-axis? So this is a very simple example, at the same time very rich example. Okay. So if you think of this as a water flowing, you can feel this waves, This is known as a vector field. This is known as a vector field. Okay. So if you put a small piece of paper here, if you put a small piece of paper, what will happen to that paper? It will flow along this direction. Okay. If you put a paper on this, it will flow in this direction. Okay. So that's how it is. This is a vector field, whereas this is the phase portrait. Because it's a continuous system, it will lines. It cannot be drawn with broken lines. These are each vectors. These are the vector field, but on the right hand side, B is known as a phase portrait. Okay. So what you conclude about okay, anyway, but can you observe why this has happened? From this, can you observe something happening on the XY plane? That's what is important. Can you see something happening? Okay, these are flowing like this is flowing like this, but what is happening here? There is something special nearby that something is happening. Okay, I will be back to here again. I will ask again to you that this is the system we are considering, right? X dot equals to 2x, x dot is 2x, and y dot is 3y. And we straightforwardly found the solution of this system. But I want to ask you, what are the equilibrium point of this system? What is an equilibrium point of a continuous system for fixed points of a... So you know already till now that if it is a discrete map, we call it a fixed point. If it is a continuous system, it is known as an equilibrium point. That is a different notation we are following. Okay. Equilibrium point in case of continuous system. So tell me the equilibrium point for this system. What is the equilibrium point? How you find the equilibrium point? Equilibrium point means nothing is changing. Nothing is changing. It is a steady state. If nothing is changing means derivative is zero. Derivative rate of change of that thing is zero. If derivative is zero, that means x dot is zero, derivative, and y dot is zero. That means 0, 0 solution, right? X and y 0. If you substitute, x 0, 0 is an equilibrium point. But then the question is, if 0, 0 is an equilibrium point, what kind of equilibrium point it will be? Is it a stable equilibrium point? That means nearby trajectories are coming towards it. Is it an unstable equilibrium point? That means nearby trajectories are going away from it. Or it is a mixed reaction state. That is, some trajectories are coming towards it, some trajectories are moving away from it. So that is known as a saddle. I already told you. So from this example, you can see this is the 0, 0 x 0, 0 equilibrium point. This is the equilibrium point, isn't it? This is the equilibrium point 0, 0. Yes, and nearby that equilibrium point only these dynamical phenomena are happening. This flow of orbits, this flow of trajectories are happening. Okay. Huh. Yeah, the same thing I told the class. Think about it. Think about it. In the fourth quadrant, y is increasing, you are saying. Don't, yeah. So you have to be very careful. You see, one thing I would say to you is if things are positive, then increasing, decreasing makes sense, a lot of sense. But if things are negative, things gets very tricky. Okay. So suppose you are in the y-axis. Suppose here in the fourth quadrant, y is less than 0 and x is greater than 0, right? So, and you had the solution y of t as y naught e to the power minus 3t, right? If I'm correct. So let me, if I'm correct. So what will happen? Y naught is negative. It's a negative quantity. This will always be positive. So the whole quantity is negative always. Yes. But you can see these guys are decreasing. As time increases, this is becoming less and less. Don't think like that. It is confusing. What I am saying is, think it is that it is a negative. As time increases, the negative number is approaching towards 0. Yes, in that sense you go. If it is increasing, decreasing, negative, you will be confused. If so, can you tell me yt is going towards 0 or away from 0? It's going towards 0. So therefore it is going towards 0. You can see. Therefore these trajectories are. Okay, that's all about the trajectories. But now I am asking you, what about this equilibrium point? You can see some are coming towards it, isn't it? This, pay attention to this, Mr. Dikhil. Yes, on the y-axis, you can see that y-axis trajectories are coming towards it, towards the equilibrium point, but the x-axis trajectories are moving outside of that equilibrium point. Nearby trajectories also are moving outside a bit. Okay. So there is a mixed nature, right? There is a mixed nature. Some trajectories are coming towards the equilibrium point. Some trajectories are moving outside of the equilibrium or away from the equilibrium. Such equilibrium points are known as, yes, they are known as the saddles, just like a horse saddle. Okay. So the equilibrium point is a saddle. So you can expect something like this. Okay. An example might be given to you and you have to compute the phase portrait, and it will be asked compute the phase portrait. Then you have to draw this diagram, and then it will be asked deduce the type of equilibrium point it is. Okay, based on this observation you should deduce that it is a saddle equilibrium. So this is something very important. Try to understand this very carefully. Okay. Brain. Yeah. Let's take the break, and after the break we will do some more examples on this 2D system. After this we will move to two-dimensional maps. Okay. So let us move to the next example. Okay, so this was the first example, right? Which was a very easy example, like x dot equals to 2x and y dot equals to 3y minus 3y. And yes, what else we got? We classified that equilibrium point at the origin to be a saddle equilibrium point, right? That was done just before the break. Now after the break, we will try to understand one more systems. Okay, another example. Now we will take a coupled linear system of 2D equation, 2D system, that is x dot is minus 4x minus 3y and y dot is equals to 2x plus 3y. Okay. My question is, can you analyze this system? This is a bit additional effort you have to do, but it is a bit more involved than the first system, isn't it? The first system was quite easy. The first system was this one. The first system was uncoupled one. X dot is 2x, y dot is minus 3y. But this system is something new. This system is new in the sense this is a coupled system. This is a coupled system. Why it is a coupled system? X dot is minus 4x minus 3y and y dot is 2x plus 3y. Yes. So my question to you is how the phase portrait will look like in this case, just like you drew in the previous case, xy. How? Suppose you started from here, here, here. So all are these initial condition. I see 1, initial condition 2, initial condition 3, initial condition 4. My question is how the solution will evolve in this case. So this is you can arrange in a matrix, right? This you can arrange in a matrix. Is it correct? Arrange in a matrix, right? The set of equations. So how it will look like? How it will look like? Suppose you take this notation capital X to be the vector x comma y, x, y. So then it will be x dot equals to some ax, where a equals to your matrix minus 4, minus 3, 2, 3. Okay. Now, depending on this matrix, can you classify the solution? Okay. First of all, what is the equilibrium? First of all, before beginning, we should start with the equilibrium point of a system. What is the equilibrium point? How you get it? Equilibrium point is given by setting what? X dot 0 and y dot equal to 0. So if you set to 0, both of them, minus 4x, sorry, minus 4x, minus 4x minus 3y equal to and 2x plus 3y equal to 0. What is the common solution for this? This implies, is it the only solution? Only one solution will exist because this is a straight line, this is a straight line, and intersection of two straight lines is a point. So you will have only one solution. So x equals to 0, that is x star equals to 0, y star equals to 0 is an equilibrium point. Okay. X star equals to 0 and y star equals to 0 is an equilibrium point, right? Then what you do? This is an equilibrium point. So 0, 0 is an equilibrium point. Last just before the break, we came to know that for the other system of equation, it was a saddle. 0, 0 was a saddle. How this will look like? What is the nature of this equilibrium? Can you tell me? Here, there are two variables. No, we are setting x dot equal to 0 and y dot equal to 0, right? From that, we got x star equal to 0, y star equal to 0 as the equilibrium point, right? Asking you how this equilibrium point will look like. I told you, it will look like the whole behavior, the dynamical behavior near this equilibrium depends on the trace and determinant. Isn't it? Trace and determinant, right? This is the figure we drew last time, no? Trace and determinant. So it will depend on the trace and determinant. So what is the trace here? Trace of A, that is tau. This is 4 plus 3, that is minus 1. What is the determinant of A? That is delta equals to 4 times 3 minus 2 into minus 3. That is minus 12 plus 6, is it? Minus 6. So you can see trace, this is the case. And what is tau square minus 4 delta? Just to know that, yeah, just to know. Yeah, okay, tau square minus 4 delta is 1 minus 4 into minus 6. Tau square minus 4 delta is positive. So by looking into this, what can you conclude? What it should be? what it should be, where it is lying, both tau and delta are negative, right? Both tau and delta are negative. So it should lie on which quadrant? Third quadrant. So third quadrant, how it will look like things here? Saddle. I drew a saddle here, right? So it should look like a saddle. Finish. So without computing anything, any difficult things, anything, you just proved that according to this chart, it should look like a saddle. Okay, it should be a saddle. 0, 0, equilibrium point should be like a saddle, equilibrium point. Saddle equilibrium point, but there is a catch. There is a catch. What is that catch? What is that catch? Here, in this example was very nice. This example was very nice because on this y-axis, these were the eigenvectors. These were the eigenvectors for your case. Can you say the matrix A for this? Can you write this equation in terms of x dot equals to ax, xy, x dot y dot equals to 0 minus 3 xy, isn't it? Miss Halima, is it correct? Yeah, like, no. So the idea is, see, just to try to understand, try to give you a bit of basic common sense in everything you try to see. Then it will be very easy to you. Okay? It is the things are very visualizing here, very visualizing. Anyway, so can you say to me that this, yes, the same ODE system we wrote in a matrix form, x dot equals to ax, right? Here, what are the eigenvalues? 2 and minus 3, because they are the diagonal matrix. So lambda 1 is 2, lambda 2 is minus 3, okay? And the eigenvectors, what are the eigenvectors for this? I will not tell how to compute eigenvectors, you already know. Try to see the basic videos, you can see how to compute eigenvectors. But the eigenvectors will be the x and y axis, okay, in this case. Therefore, the image was very clean, the image was very nice, okay? But in this case, the case you are studying right now, that is this case, if it is a saddle orbit, but what should be the eigenvectors in this case? You should find the eigenvectors. Do you think it will be like this, just like the previous example? No, it won't be, okay? So how it will look like? That's my question to you. So this is what we are trying to do in this lecture. This is what we are trying to do in this lecture, okay? So you have this matrix, you already know that it is a saddle equilibrium point, but how you can draw the phase portrait? Your aim is to draw the phase portrait. Just your intuitions and mind, okay? How you do it? Can you answer me? Can you find the eigenvectors? Can you find the eigenvector for this matrix? Can you find the eigenvalues lambda 1 and lambda 2 for this matrix? Anyone can tell me? What is the eigenvalue? X1? You very careful, like which mat? This one. This is the A matrix, right? X dot equals to AX. I told you, like the eigenvalues of A will determine the qualitative behavior of the system, how things will flow around. How things flow. How things flow. What are the, just tell me the eigenvalues and corresponding eigenvectors. That's it I want from you. Let us see this beautiful application. Okay. Oh no. Okay. Fine. I'll go to a new page. I'll go to a new page and you have to tell me all the eigenvalues. Can you tell me the eigenvalues? Minus 3. V1 is corresponding what I V1 is 3 minus 1, right? Okay, then lambda 2 is 2, V2 is 1 minus 2, right? Okay, based on that, let us draw the phase portrait. Based on that, let us draw the phase portrait. 0, 0 is the fixed point that I am giving you as a big dot. Okay, now I am asking you, you already know from the determinant value that both tau and delta were less than 0, and from that we confirmed that it is a saddle equilibrium point. That means something will be close to them and something will be moving away from them. That's the idea. Yes, saddle equilibrium point. Now, based on these eigenvalues, how we can mark the solution? Okay. Now, remember the fact I told you in the 1D continuous system that a fixed point, an equilibrium point is stable if eigenvalue is less than 0. The real part of eigenvalue is less than 0, isn't it? In 1D ODE system, yes, we had an example, right? Equilibrium point is stable. All eigenvalues have real part less than 0. This is the most important concept, okay? An equilibrium point is stable. That means all the trajectories nearby will converge to the equilibrium if the real part of the eigenvalue is less than 0. If the equilibrium point is unstable, okay, equilibrium point is said to be unstable if all eigenvalues is the opposite of it. All the eigenvalues have real part greater than 0. Yes, then there is a mixed trait, that is saddle. An equilibrium point is saddle if real part of one eigenvalue is less than 0, that is it has a stable component that is come closer, and the other component, that is lambda 2 real part, should be greater than 0. That is an unstable component. That's the definition. For no, real part only we need. The eigenvalue can be complex, right? In that case, you can need to see the real part. Yes. So here automatically it is real, so that complex part is 0, but it is real. Yes. So this part is the stable part and this part is the unstable part. So you can see this is of a mixed nature, mixed type. Okay. So our equilibrium is a saddle equilibrium, right? Can you see what are the eigenvalues here? The real part, one is less than 0 and another is greater than 0. Can you see? Can you see that? See, here the real part is less than 0, that this is the stable direction. So this is the stable direction, stable eigenvector or stable eigendirection. Okay. And lambda 2 equals to 2. This is the case where it is the unstable eigenvalue, right? Unstable case. Real part is greater than 0. So this is the unstable eigendirection. So now you know along which direction, now you know in xy plane, which direction is stable and which direction is unstable. That is why I told you to compute the eigenvectors. That is why eigenvectors and eigenvalues are so important. Why we computed eigenvalues? Because eigenvalues tell you about the equilibrium point, whether it is stable or unstable. Why we compute? Because they tell the trajectories will come closer or move away from that point. You can see whatever we are computing is not going in waste. Everything is being used. Okay. Now, along which can we plot this? That's the question. That's the main question we have here. 3 minus 1. Let's plot 3 minus 1. Where 3 minus 1 is? Can you say x is 3, that is positive somewhere here, and y is minus 1 somewhere here. So let us do a point here, somewhere here. So we can connect it to the origin and sketch it. Okay, fine. Let me draw it. Happy with this? Happy with this one? How it looks? That's the. Okay. So this is one direction, but whether it is stable, if you see, if you move along this direction, should you come closer or move up the equilibrium point? What do you think? Along this curve. Hmm? This is the direction I just drew. Why? Think carefully. Think carefully. Why? This vector is this vector, right? What is the corresponding eigenvalue? To this eigenvector, the corresponding eigenvalue is -3. Yes, and -3 is a stable eigenvalue, right? Real part is less than 0. So trajectories will come closer to the equilibrium point, right? Yes, if it is stable, what it means? It will come closer like this. Yeah, this is the eigenvector I drew. Yes, the story is unfolding. But let us do the simple case first. That is, let us see the case at only at the eigenvector. Happy with this one? Since it is stable, I will just draw it in blue. That's my convention. Okay. Now let us do, this part is completed. Now let us do the second part. That is lambda 2 equals to 2, where the V2 is 1 comma -2. X equals to 1. Think of this as X component. Think of this as Y component. X component is 1. 1 should be less than 3, right? So 1 is here. Y component is -2, which is bigger than this. So yeah, it will be below this. So somewhere here. Yes. So let us try to draw this. Let us try to draw this. How it will be. Yeah, maybe. Yes. So okay. Wait. So this this is an eigenvector, right? So this is V1, this is V2, right? Now tell me, like along this eigenvector, whether it should converge towards the equilibrium point or move away. What do you think? See, this is the eigenvector we just drew, and the eigenvalue is 2, that is greater than 0. Greater than 0, I told you, if it is unstable. Yes, if it is unstable, it should move away, right, from this equilibrium point. So move away means it should be on both directions like this. Can you see this? Yes. Now you are done. Now you are done. Now you have to just use your basic common sense. Now you have to just use basic common sense. Now can you tell me how the nearby trajectory looks like? Can you tell me how nearby trajectory looks like? Hmm? Yes. How the nearby trajectory looks like? Think of it. See, hmm? Assume that you are traveling, assume that you are on this plane, okay? And these are the direct, if you are on this line, you will straightforwardly, it will kick you here. If you are here, it will straightforwardly kick you here, okay? Got it? If you are on this curve, it will push you towards origin. If you are here, it will push you towards origin, right? Done? Yes. Now I am saying, oh no. Let me concentrate on this. Yeah. Now I'm saying to you that if you are traveling along this line, how it will look like? isn't it? It should travel along this, right? Because this is the wind here, this is the wind here. Are you getting the idea? So it should travel something like this, right? Isn't it? Yes. How here it should travel? How things here should look like? Here, you are slowly traveling, but you cannot travel like this. You cannot travel like this. Can you travel like this? No. Why? Because there is a wind here. So you will be attracted towards this. Yes. At the same time, it will be attracting you. So it will move like this, right? Can you think of this as a magnet? Yes. Now let us okay. Let us come to this figure, this part somewhere here, how the trajectory looks like. You are coming here and going away, right? So nearby this, it should look like this, isn't it? Can you see the wind pattern? Yes. Understanding that, right? How the wind pattern will look like here? It should go like this and come here back. It should go like this and return back here. Yes. So this exactly same pattern, I will share the note to you. This is how saddle looks. This is how saddle equilibrium looks nearby the face portrait. Okay. In the face portrait, how saddle equilibrium looks. It is not that simple. Okay. You can see that some trajectories are coming towards it, whereas some trajectories are moving outside of it. And nearby, it is more interesting. So this these notes will be given to you today. Okay. So you can see this PDF image here. So you can read the text here and understand if you did not get this. It is written in a good way. Okay, that is fine. Let us come to something interesting even more. This is all about graphic. We did not do any math, right? Did you do any math? No, it is all about graphic, like all about computing eigenvalue, eigenvector. So what we did, first we compute eigenvalue, eigenvector, V1, V2, then classified the equilibrium point. We classified the equilibrium point. Okay. Fourth, draw the face portrait. We drew the face portrait. Okay, drew the face portrait and the vectors. Isn't it? Yes, this is the face portrait. So in exam, if I give you this system and I ask you compute the face portrait, then you have to draw this one. Okay, that means you have to compute the you have to do all these steps. Okay, that's the idea. So you can expect, since a lot of activities are involved, you can expect to be a 10 marks or some question like this. Okay. Okay. Something more is there. Something interesting is there even more. What can we do mathematically? What can we do mathematically? Can we make sense mathematically to this? Yes, we can. So therefore, while you were trying, I did this. I did write all this. Let us go through this a bit. This is also in the notes. You can read it. Okay. Okay. What we did, our aim, first of all, don't look into all these notes. See my cursor. Okay. Our aim is to solve this equation, right? X dot equals to AX. This is the 2D system, right? 2D dynamical system, 2D continuous system, continuous system. Yes. Now, my aim is my aim is that you already know that eigenvalue and eigenvector play a huge role, right, in reducing the solution. So they should appear in the solution. Right? If eigenvalue and eigenvector play such an important role, they should appear in your solution. Can we compute the solution? That's the idea. And the idea is for a linear 2D linear system, you can compute it explicitly. But the moment, like as Mr. Anandik will give the talk on Rosler system, Mr. Jayadis group can give the talk on Chua system, and Miss Remia here, they can give on Inmerse Rose for project topics. You will soon realize that you cannot compute the solutions explicitly like you do here. You have the solution explicitly only because these are linear ODEs. These are linear systems. Okay. For linear system, you can compute you can make some sense. Okay. Anyway, so to do that, what we do, we compute the eigenvalues of A, lambda of A, and compute the corresponding eigenvector, that is U, to each eigenvalue lambda. Yes. So if lambda is an eigenvalue, what does it mean? AU equals to lambda U. Yes. If lambda is an eigenvector, eigenvalue corresponding to, and the corresponding eigenvector is U. AU equals to lambda U. What is lambda here? Eigenvalue. What is U here? Corresponding to lambda, what is the eigenvector? That is U. Okay, AX equal to lambda X, AU is lambda U. Yes. Now my question is, can you compute what is A into V? AV is the right hand side, right? This one, AX. Yes. Yes, AV. AV is A lambda, A e to the power lambda TU. Don't look into the other things. Just follow my cursor. You will be a bit confused if you look into downstairs. Just follow my cursor. Okay. We are here. Everyone with me? Everyone with me. Okay. Now I can take e to the power lambda t outside, right? Just as the multiplication. Yes. So e to the power lambda t into A into U. Yes. What do you know about A into U? AU is lambda U, right? From this equation, from equation 1. So you substitute lambda U here. So you got this equation, right? Lambda e to the power lambda TU. Yes. Okay. Yes, that's the concept we used here. So, but the same thing, this is one star equation, forget about this. Okay. Now, you already know that Vt is e to the power lambda Tu, right? This is the assumption. This is the assumption. Suppose this is the case. Then can you take the derivative of this V dot T? Can you take the derivative of this guy? Follow my cursor. It will be lambda e to the power lambda Tu. Yes, you got this. Fine. Now using star, what you get? AVT is the same quantity as you got here, right? From star. Yes. This guy is the same quantity as this guy. Yes. Yes. The derivative of V is lambda e to the power lambda Tu, but the same quantity you are getting when you compute A into V. Okay. So therefore you proved that V dot equals to AV. That means this guy which you had assumed is a solution. This guy is a solution to this system of equation. Okay. Is it? Huh? Yeah. So maybe it is a bit tricky for you to understand, but I think through the notes you can understand a bit more clearly. It's nothing. It's just that you assume. See, I will tell you again. You don't know the solution, the red part, and you just substituted. You computed V dot. From this, you computed what is V dot and what is AV. You computed. What is the case? Later, you found that both of these quantities are the same. V dot and AV are the same. If V dot and AV are the same, what you conclude? V dot equals to AV. What you conclude? V is a solution to this. V is a solution to this. So therefore, V equals to e to the power lambda t into U is a solution. What is that noise? You're thinking that noise is something else? Think it is a noise only. Don't think of it as something else. Okay. Yeah. So yes, let us be back. So V of lambda Tu. Okay. V of t is e to the power lambda Tu. So you know there are two eigenvalues, lambda 1 and lambda 2, right? Okay. Anyway, let us be back. So when you took lambda 1 eigenvalue and its corresponding, you have this expression as V1, right? And similarly, corresponding to lambda 2, if you have U2, V2. So these two are the solutions. These two are the solutions. And I won't go to complications, but if you consider the linear combination of those two, that is also a solution. That is a linear combination. That is some combination of this solution and some constant combination of this. That is also a solution. This is a bit mathematically involved, but I just wanted you to show that this is the case. And what you drew here, what you drew, all the lines, all the curves, is actually following this equation. Okay. Huh? That is the solution. That is representing the solution. That means this you drew, right? This you drew, right? If you start from this guy, then this is the curve which represents Vt. This is Vt. Now this curve which you drew here, that is also Vt. Okay. You will get different curves depending on different starting points. Okay. Are you happy with that? So those who are not able to understand, it's given as an example 7.5 in the notes. I will share this today itself. Okay. Fine. All right. Yeah, so there are two more examples I want to cover. There are two more examples just to make you understand how it looks. Okay. You're okay, right? Come on. Like, okay, don't worry about it. I will just cover two examples and it will be over. It's interesting, no? The examples. No, not interesting. Okay, let us see this example. One more example. So what are we doing here? We are considering example after example, but what are we doing here? Can you say what are we doing here? See what we did here. We took one example, very simple looking example, and we discovered that it looks like this. Okay. Then we took another example, this one, and we discovered that it looks like this. Now we are taking another example and want to see how it looks. I'm just giving you a feel that changing the matrix element A is giving you different qualitative solutions. The flow is getting different. No, we took no. It depends how you look at it. I see I wrote this here, x dot equal to ax. Huh? Here, this one, right? This example, right? Hmm? Yes. You can write this, see my cursor. Can you see my cursor? Yes, that is written as a matrix. Okay, can you predict? I have given you two examples. Can you predict how it looks like? How the solution look like for this? Write it in matrix form, no? X dot y dot equals to 3, 1, 0, 3. XY, right? What do you think? What do you think will be the case here? It is a special case. It is a special case. Something special is happening here. Okay, can you tell me what is the trace? This is the matrix A, right? Can you tell me what is the trace of matrix A? That is tau. That is 6. What is the determinant of A? 3 into 3. minus 0 into 1, 9. So trace is greater than 0 and determinant is greater than 0. So it will lie on the first quadrant. And you know that in the first quadrant, just by computing sign will not help you. You have to find tau square minus 4 delta. Because so you have two possibilities now, right? Tau and delta is positive. That means you have two possibilities. You can have spirals. Yes, both are the cases. Isn't it? See the first quadrant. See the first quadrant. You can have two possibilities. Either it can be unstable nodes or it can be unstable spirals. Yes. Okay with you? What is tau square minus 4 delta? Tau square is 36 minus 4 into delta, 9. That is 36, that is 0. So it is lying exactly on the curve. It is lying exactly on the curve. Okay. What happens in that? What happens? Can you compute eigenvalues? Compute eigenvalues and eigenvectors. You don't need to compute eigenvalues at all. It is already being given to you for free. Isn't it? It's a upper triangular matrix, right? It's an upper triangular matrix. So the diagonal elements will be the eigenvalues. Upper triangular matrix, because this is 0. Above that, below the diagonal, the elements are 0. Below this diagonal, the elements are 0. Therefore, the eigenvalues are given by the diagonals. So lambda 1 is 3, lambda 2 is also 3. So it's an eigenvalue with repetition. Multiplicity of eigenvalue 3 is 2. 2 times it is repeated. Lambda 1. Lambda 1, 3 is repeating itself 2 times. No. That is what it is saying, repeated eigenvalue. Come. Can you compute? Convince yourself that you will get the eigenvector to be the same for these two guys. The eigenvector is 1, 0. Yes, the eigenvector is 1, 0. Okay. So let us try to draw the phase portrait. How it looks. X, Y. 0, 0 is the equilibrium point, isn't it? 0, 0 is the point. And what eigenvalues you got? You got eigenvalues to be? What is the eigenvalue? 3. It is positive or not? Positive. So it is stable or unstable? Yeah, because it is positive. Yes. So 0, 0 will be unstable. 0, 0 is unstable. Both of the eigenvalues are greater than 0. Both eigenvalues are greater than 0, right? And what I told here, equilibrium point is unstable if all eigenvalues have real part greater than 0. So it is unstable equilibrium point. What is the eigenvector here? 1, 0. How to draw 1, 0 eigenvector? How to draw 1, 0 eigenvector? X equal to 1, right? Y equal to 0. So 1, 0 is lying here. Yes. What should be the direction? 0, 0 is unstable. Should it go away from 0, 0 or towards 0, 0? Away from 0, 0, right? So how we will draw? So I will draw like this. It is going like this. Isn't it? Yes. And try to find a general solution. Try to convince yourself that it will look something like it won't be linear to you. It will be like check the notebook, like it will be something like this. It will be symmetric if you see. And similarly, you will have something like this again. And this also like. Okay, so it will look something like this in the notes, which I'll give it to you today. It is moving outside. Okay, try to read this. So you can take some other initial condition, but you understood why it is moving outside, right? Because both lambda 1 equal to 3 greater than 0, lambda 2 equal to 3 greater than 0. Both are unstable according to our stability theorem, right? You got it. Fine. Last example. Okay, just this simple example. Just this simple example. How can you do this? Can you tell me? Like this is x dot y dot right in matrix form. 0, 1, -1, 0, right? Yes. So this is matrix A, right? Can you compute the trace? 0. Can you compute the determinant of A? 1. So determinant equal to 1, trace is 0. Where it will lie? So tau equals to 0 and delta equals to 1. Can you say where it will lie? On this axis, right? On this axis, isn't it? Yes. If it is lying on this axis, how it should look like? It should look like circles, like periodic orbits, limit cycles. Okay. So periodic orbits. So that's the idea. So without that, you just came to know that they 0, 0 is center. The equilibrium point is a center. Okay. How it will look in phase space? Can anyone give me an idea? Okay. What are the eigenvalues in this case? That row will tell me. What are the eigen? That row will tell me. Now only. Within 2 minutes, you tell what are the eigenvalues. What are the eigenvalues? So one is I and minus I. Yes. Now the eigenvalues are complex. So how you can analyze the solutions? That is the question. How? You are stuck. How you will do? Think about it. And last example. So you know that the solution previously I found, like if a solution to x dot equals to ax is given by u e to the power lambda 1 t. Yes, the eigenvector e to the power lambda 1 t. What is the eigenvector here? Don't need to compute, it will be complex. Okay, but anyway, you now know that e to the power it it will be e to the power it. You know e to the power it is cos t plus I sin t. Yes, 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 something like that. And it is, I think it will, I will leave this as a assignment for you. Okay, I will leave this as an assignment for you. Just I wanted to tell you that cos and sin are involved in the solution, so you can get the solution xt, which is, you can see in the notes, it will be just a combination of cos t and sin t. Okay, so when you draw the things on the face portrait x y, they will appear as this. Okay, they will appear as this solutions. Of course, you have to start from here, one initial condition, it will be like this. If you start from one initial condition, it will go like this and come back. This is another initial condition, go back and come back. So what is making the radius to increase? Okay, that you have to see. Okay, this is what the phase portrait looks like for the center. So your job is to think why this is the case. I might be a bit faster in showing this, that this is the case, and suddenly you might not grasp it. But I suggest that through these notes, try to understand each and every line. All the examples are given here. Okay, try to understand and get this graph. These are very important. These are very important. So you know already that the first test will be on Tuesday next week, 11:30 to 12:30. The syllabus is 1D map. Only 1D maps. Only 1D maps. I did not take continuous systems. Only 1D maps. Okay. Can we decide the test for now?